So you might think a little bit about why this is true. But this is, first, I just want to point out that this is like the fundamental equation of this whole section. So you kind of want to burn this into your brain, that this is the equation that we're going to be using for this whole section for all of these problems. This is where everything comes from. So get this into your brain. Okay. And so where does it come from? Basically, if you were to multiply these out, remember this has all of those coefficients, those decimals, and those decimals represented how much of one good I needed to produce another good. If you multiply this had the variables representing the goods. So if I multiply these out, I'm going to get a bunch of, I'm basically going to get things like, oh, I don't know, 0.2 times lumber plus 0.55 times oil, for example. And that's going to represent how much lumber and oil is needed to produce lumber. AKA, it's going to tell me how much extra lumber I need. In addition to, if I add in this D, I need to shoot for this much lumber. So it's basically going to tell me how much additional lumber I need plus the amount of lumber that I want. And that's going to tell me my production schedule. I don't know, maybe that was not the best explanation, but maybe I'll try it backwards. D is how much I want of the goods. So I start with that. And then what I need to add to that is the additional amount of the goods that I need to produce that amount. And multiplying these two together will give me exactly those expressions. Because the first row of this is the amount of lumber needed to produce the two goods. And the second row is the amount of oil. And so when I multiply them out, that's exactly what I'll get. Okay, so maybe I bungled that explanation a little bit, but on our activity, it'll walk you through one of these and give you these explanations as well. So I don't know. Here's a better thought too. Let me pause and ask, are there any questions? Hopefully I'm not being too confusing. Always hard to gauge when I'm teaching online how much I am or am not getting through. So.
I have a question.
Yes.
I'm not totally sure when it comes to how we produce this technology matrix.
Yes.
Is it going to matter the specific order of the entries?
Yes.
Okay.
Yeah, so the order totally matters. So that's why I sort of outlined, that's why I sort of wrote it down the way I did. I'll do it again. So I had this matrix I was filling in, and for us, it's a 2x2. And so I had a lumber row and an oil row and a lumber column and an oil column. And so it really matters which numbers go where. If you get them in the wrong spot, it will change the answer, and it won't be quite right. So the way we're setting it up, we have to do it this way. And the idea is when I'm in the row, I'm asking, let me double check I'm saying this in the right order. It's one thing you can never be too careful about. Yeah, so if I want to produce 1 unit of lumber, then how much lumber do I need is what we're going to ask. So when I'm in the row, I'm asking how much lumber does it take to produce the thing in the column. So the amount of lumber it takes to produce 1 lumber was 0.2. And the amount of lumber to produce 1 unit of oil was this 0.55. So the order matters. So you should ask yourself, when I'm in the row, label the rows by the goods and ask, how much of this good did it take to produce this good? And that'll give you the correct ordering. So again, our technology matrix, the amount of oil to produce 1 unit of lumber was 0.4, and the amount of oil to produce 1 oil was 0.1. So it should be this.
Okay, thank you.
Yep. So yeah, I'll stress that again. The order very much, that you put in the elements very much matters.
And then you knew to put lumber before oil because. So
that's just a decision that I've made. Okay. That's been made in the way I'm writing down the problem for you guys. Usually in the problems, it'll be clear which way to order them.
Okay. It'll
either just straight up tell you, write them in this order, or they're just given to you in a certain order, so just use that order. So it should be clear.
Okay.
Yeah, that's a good question though. Thank you. Any other questions? Okay. So That's technology matrix. And here's our equation where everything is going to come from. So I have this equation, which is just sort of defined by the way the problem is set up. That's where this comes from. And so now our question is, in our problem, currently we need to find x. Because we know A and we know D, but x just had variables in it, so we need to find x. We need to solve for this. But this is now a matrix equation, and we just learned in the past section how to solve a matrix equation, because we can do things like add and subtract matrices, and we can multiply matrices, and we can divide by matrices, which really means multiply by an inverse of a matrix. So what we're going to do is solve this for x. So we're going to solve for x. I'm going to show you how it works just because there's sort of a tricky step involved, and I want to make sure it's clear how that works, so the formulas don't just seem like magic. So let's solve this for x. So we have x equals ax plus b, and everything here is a matrix. Everything's a matrix, so there are no numbers. These are all just matrices in this equation. So I want to get x by itself. So maybe a first thing that would be helpful would be get all the x terms on the same side of the equation. So like I have this ax and this x, but they're separated by the equals. So maybe I'm going to move this ax over here so that the x's are all on one side together. That's a good first step. So let's subtract ax from both sides. We'll get x minus ax equals b. And this is a subtraction of matrices, but it's okay, it all makes sense. This is defined, everything's fine. So I can subtract ax from both sides and get x minus ax equals b. Okay, so all the x terms are on one side. Now it's sort of annoying, I have two x terms. I would really like to get just one x on this side. And the way I'm gonna do that is by factoring. We saw an example of factoring a couple weeks ago when we did the elimination method. We're gonna do it again here. It turns out it works for matrices again because we have the distributive property. And it's just a little tricky here. If I factor out x, what's left over? You know, I wanna write something in parentheses times x equals b. So something times x equals x minus ax. What should go into parentheses? That's the question. You know, what would give me the equality here? Well, maybe there's going to be a minus a, because certainly minus a times x is minus ax. That's fine. But what's going to get me just this x term? Well, what times x equals x? Well, that's going to be the identity matrix. Remember, the identity matrix is basically like the number 1 here in the sense that multiplying by the identity doesn't change anything. So if I distribute this out and do I times x, I'm just going to get x. I'm going to get back where I started. So I minus a times x is the same thing as x minus ax. I just distribute this out. Okay, so we're allowed to factor in matrices, and this is sort of how it can work. This is one example. So now I have this equation. So we're almost there. I just want to get x by itself. How do I want to get x by itself? Well, I need to get rid of this I minus a. And this is multiplication between I minus a and x. So to undo the multiplication, I sort of want to divide. But we know that division for matrices is really the same thing as multiplying by the inverse of a matrix. So I want to multiply by the inverse of I minus a. So that's what I'm going to do. If I do that on the left side, the I minus a and the I minus a inverse will cancel, and I'll just get x. Then on the right side, I'm going to have I minus a inverse times d. And we just have to be really careful again, because notice I minus a is on the left of x. So when I multiply I minus a inverse, I'm going to do it on the left. So I better write I minus a inverse on the left of d, like this. It has to be to the left of d. Because again, we have this issue where matrix multiplication is not commutative. So a times b is different from b times a. The order matters. So if I were to write this on the right side, I wouldn't get the same thing, and it would be wrong. So we have to be careful that this goes on the left of d. Okay, we ran into that issue last section. There were some, I talked about that at the board, and there was a couple problems on your activity about that. So just to remind you, order of multiplication matters, so we better multiply on the left. But that gives us this. We have now solved for x. So x is identity matrix minus a inverse times d. That's how we can solve for x. So when you guys are working on a problem like this and you need to find x, you can sort of skip this derivation here and just skip to this formula. You could treat this as a formula that you could memorize if you want and then apply. But I wanted to show you how to solve these because it's important to put this, I don't want to just pull this out of thin air. Is one reason. Another thing is it's good to practice this stuff because you guys will need to be able to do it. And also one other thing is we're going to solve this later on for D and it'll be slightly different. So anyway, I just wanted to walk through these steps because it's a good exercise. But know this formula. You will want to know this well so that we can apply it. So let's go ahead and apply it now in our situation to solve out this problem. So you can get a feel for how all this works. So I'll rewrite this formula up here. X equals I minus A inverse times D. And now we're going to solve it with our current problem. So remember that A was 0.2, 0.55, 0.4, and 0.1. And D was 10, 20. Okay. So the first thing I might want to do, I want to simplify this. I might want to find I minus A first. So let's do that. Let's do I minus A. We could break this down into steps. First step, find I minus A. So I minus A is 1, 0, 0, 1 is I, minus this A matrix, 0.2, 0.55, 0.4, 0.1. And now I just simplify this subtraction. 1 minus 0.2 is 0.8. 0 minus 0.55 is 0.45. Or sorry, no, it's not. It's negative 0.55. My bad. 0 minus 0.55 is negative 0.55. Okay. 0 minus 0.4 is negative 0.4. And 1 minus 0.1 is 0.9. Okay. So if you can't already tell, we're going to have a lot of decimals in this section. And that's just something we're going to have to be able to deal with. You guys have it easier since we're online. You guys get to use calculators. So it won't be as bad as it might have been for my students in person in the spring. But anyway, you'll have to be comfortable with working with decimals. They're going to be all over the place in this section. That's just sort of the nature of these problems, at least in your book. Anyhow, this is my matrix I minus A. Now I need to find the inverse of this. And so we have two options. This is a 2 by 2 matrix. So I could either use our algorithm that I taught you guys last week, where I row reduce the augmented matrix, or you could use our formula that was on your activity for a 2 by 2, where I used the determinant to calculate the inverse. And I'm going to do it that way, just because it's faster, and this is a 2 by 2, so I can do it. But if this was like a 3 by 3 or something, we'd have to use the algorithm and row reduce. Just be aware of that. But so the determinant of this is 0.8 times 0.9 minus the negative 0.55 times the negative 0.4. 0.8 times 0.9 is, so 0.8 times 0.9 is 0.72. And 0.4 times 0.55, I think that is 0.22. I think that's 0.22. Hopefully I did that right. And so what's 0.72 minus 0.22? This is the determinant. That's 0.5. This is why I deliberately chose our numbers this way. Turns out the determinant of this is 0.5. So my determinant formula says to take 1 over 0.5 times, and then according to the formula, I'm supposed to swap these two, and then take the negatives of these guys. So again, if this seems like, if what I just did was, you don't know where this just came from, look back at your activity 6.2a, I think it is. I forget which problem, but look on there, there was a bunch of problems about using this determinant formula to find the inverse. And so we could simplify this a little bit.